reduced row echelon form, RREF. Number 12 is a 3x4. Number 20, you were just, sorry, those of you that didn't realize it, just writing the augmented matrix. Shout out. Just writing the augmented matrix. So the variable coefficients, the zeros for anybody who is missing, and then the constants, you can either do a dotted line or a solid line. Both are good. Number 36, it started to be weird. It was like, hey, look, I went here. Do you know how? And can you fill in the box? They were getting their ones, and how do we always get ones? We divide. So they divided everything by a -3. Check it. I don't think they wrote this off to the side. I think you had to figure it out. They divided by -3, divided by -3. Oh, haha, divide by -3, and you fill in the box with a -4. They were getting their 1. Dividing everything by a -3 or multiplying by -1/3. Number 46. For every column where you have a 1 established, there need to be zeros everywhere else to be in RREF. So 1 zeros, 1 zeros, 1. So it's not in RREF because for this 1, we don't have only other zeros. So we can't say RREF, we can only say REF. 1s and zeros below, but for every 1, not every other element is 0. Remember, this column doesn't matter. He's the answers. But that 1 should have been made a 0 to be in RREF. Number 78, the full shabam. You put it in an augmented matrix. You have your 1, you get your 0. Oh, when you got your 0, what happened? Everything canceled. But hold on, Adam just said y equals a. I thought we always let z equal a. We don't have z's. Yeah, so we let whoever's row that is. Or I should say whoever's column that is. We missed the 1, so therefore who was there? Y equals a. So y equals a, and then we go ahead and plug in and say, okay, well, x minus 3a is equal to 5. Add it. So therefore we have 3a plus 5 and a. Whenever a whole row goes out, that variable becomes an a. And then we back substitute. We back substitute. Number 102. Maybe it sounds awful, but guys, the clues, thank you, Adam, actually. I wouldn't have known what the problem was, except we talked about it last week a few times after school, or at least one day after school. It said you needed the zoo. Is this the zoo problem? The zoo needed $2 million. But they couldn't just go to one bank and be like, hey, give me $2 million. The bank was like, no, I'll give you this much. They actually had to go to 3 different institutions to get that $2 million. So how much they had in the X and the Y and the Z all needed to be $2 million. The interest at each of them, man, they would have loved to have all $2 million at 8%, but they weren't able to. So they had to take out some higher interest loans. Maybe they should have waited and saved. Take your personal finance class. Definitely teaches you about debt. Anyway, you have your 8%, you have your 9%, and you have your 12% for each of the different amounts. They told you all that interest, the interest payment each year, is $186,000. It's like mortgage payment, but times tons more. And then it says the amount in the 8% is twice the amount in the 12%. So I would have said x equals 2z, but you had to move it over to this side so that you could have it all nice and pretty and lined up for your matrices. Now, guys, they didn't do an awful job, except, man, they weren't being very considerate of doing things by hand. Who wanted to actually deal with decimals? So how do you get rid of decimals? If you have 2 places, let's multiply everybody by 10. No, 100, right? Because then that's an 8, that's a 9, that's a 12, that's a 1,860,000. But it is what it is. 18 million? Oh, 2 places. Yeah. Sorry, 18,600,000. Bleh. But the nice thing is you had your 1. You just would have multiplied by -8 row 1 plus row 2 if you had gotten rid of your decimals. It does end up eventually working out. They actually were lazy and said, forget it, I'm tired. And they didn't do RREF, if you notice. They just did, whew, we got one, 600,000, go back, plug in. And they got the other one, and then they got the other one. Final result being, oh, where's their answer? Oh, sorry. 1.2 million at 8%, 200,000 at 9%, and 600,000 at 12%. Is that the last one? Yeah. Okay, I'm ready. Any questions on 8.1? Those of you guys that were absent, notes should be on the videos. Examples should be on the videos from last week. The nice thing is, once again, you only missed one section, even though it was a big one. Yeah. 69. Look at Wyatt, ready to go with a homework question. Anything else besides 69? 79? Yeah. Let me go ahead and freeze the screen on 78. That way you can peek at it, Austin. And I'll go get pictures of 69 and 79. 69 and 79. It's not on the first page, though. Second page? Third page. All right. 69 looks like a 3 by 3. 79 looks like sorry, getting a picture of 69, got it? And 79, ¿dónde está? Ooh, 79's order is gross. He's one of those funny ones because he has 3 variables, but only how many equations? Only 2. Okay. As I get this ready for you guys, I think, Austin, did you have enough time with 78? Okay, cool. Let me go ahead and put up, because I want to write some augmented matrices, etc. Let me put up for you guys the first page of section 8.2 notes, because you don't need to write the augmented matrices. You don't really need me to show you how to write the augmented matrices. So let me do some work on getting these problems ready to go as you guys start taking section 8.2 notes, and then we'll come back. Matrix operations. It actually starts off super, super, super basic. Like, hey, you know what? These guys have names. And you're like, no, really. We already found that out yesterday. Actually, not yesterday. Probably the first day, right? So Wednesday. Anyway, go ahead and start, and let me get my augmented matrices already. Ready. All right, we should be pretty close to getting this down. Once again, guys, as you're writing down matrix operations, basically they're saying in order for 2 matrices to be equal, they have to have the same size, aka the same order, rows and columns, and the same entries, which seems super basic, like, oh, it needs to be the same. Yeah, but like vectors, same magnitude, same direction, there were 2 things that needed to be the same, and with matrices, it's basically the same idea. The order must be the same. And the same, like the same number of rows with the same number of rows, same number of columns with the same number of columns, they must correspond, and then the same corresponding entries. So if there is an equal sign, and if they give you something like x, -1, -3, 0, we know that x has to be a 2. There's no way for 2 matrices to be equal and the entries not to line up. I know that sounds weird, but it's true. Now, it could be something where we had a 4 and a -2, 6 and a 0. in front. There are other ways of writing, as in factoring out or bringing in fractions to where it ends up equaling the same. But then the other thing is to remind you guys that when we have these little notations of A11, A12, A21, A22, remember it's row first and then column. First row, first column, first row, second column, second row, first column, second row, second column. So that's all that's going on there. Let's peek really quickly at those two homework questions. Zoop, zoop, there they are. And see what's going on. I already saw I have a 1 and I have a 0, so actually to finish off column 1, I would have just gone attacking this third row. The ironic thing is actually we can just do row 1 plus row 3 to get rid of that one, because this is already the opposite of that. So R1 plus R3 to get our 0. So 1 minus 1, 2, sorry, 1 plus negative 1. 2 plus 1, negative 3 plus negative 1. And then negative 28 plus negative 5 would be negative 33. We have our first column done. Problem is now we need a second column, yeah? Guys, remind me real quick because it's been like a long weekend. What do we go trying to get first whenever we get to a new column? We try to get a 1. And where does the column, or sorry, what row does the 1 need to happen in the second column? The second one. We need our diagonal set of 1s. How do we get 1s? We divide. So I'm going to do 1/4, row 2. 0 divided by anything or times anything is 0. 4 divided by 4 is 1. 2 divided by 4 is a half. 0 divided by 4 is 0. My other rows were fine. I wasn't allowed to touch them yet because they weren't my next objective. My next objective was just that 1. But as soon as I have the 1, now what do I go looking for? Getting the zeros. So you get zeros in row 1 and in row 3. And so we multiply whatever row has the 1 by the opposite coefficient. So negative 2 row 2 plus row 1. And then negative 3 row 2 plus row 3. Some of you guys that already got this one to work out, if you can just be keeping me honest and making sure nothing's going wrong. I have my 1, 0, 0. Everything stays the same. My row with the 1, I'm going to be using him, so I just copy him down. Negative 2 times 0 is 0 plus 1. Got it. Negative 2 times 1 plus 2 is 0. Negative 2 times a half is negative 1. Minus 3 is negative 4. Negative 2 times 0 is 0, so that guy's going to stay the same when I add. Negative 3 times 0 plus 0 is 0. Negative 3 times 1 plus 3 is 0. Negative 3 times a half is negative 3 halves minus, my head's going to make this guy 8 halves. So negative 3 halves minus 8 halves, minus? Yeah, is negative 11 halves. And then negative 3 times 0, this guy gets to stay the same. It's time to move to our last and final column, which is the third column. And the third column, once again, needs his 1 before he gets anything else. And so his 1, we're aiming for this side right here. We get it by dividing or multiplying by the reciprocal. So negative 2/11 row 3 will get us that 1. But times 0 is 0. Times 0 is 0. That's super nice. When I multiply by the reciprocal, I get my 1. Now negative 33 times negative 2 over 11. 11 and 33 reduce to be negative 3 times negative 2. It's a positive 6. Actually ends up being a nice number. These ones stay the same, so 1, 0, negative 4, negative 28, because they are not my objective. To finish this guy off and get our REF and be done, all I have to do is get my zeros. And how I do that is I choose the row where my 1 is, and I say, hey, let's multiply that row times the opposite. So 4 times row 3 plus row 1 will get rid of that guy, and negative 1/2 row 3 plus row 2 will get rid of that guy, and I'll be done. So I keep this guy 0, 0, 1, 6. And P.S., don't we already know that z equals 6? Sweet. Now we're just looking for x and y, because 1z equals 6. 4 times 0 plus 1, still just 1. 4 times 0 plus 0. 4 times 1 minus 4. 4 times 6 is 24, minus 28 is negative 4. Now I know x is negative 4. Last one. Negative 1/2 times 0 plus 0. Negative 1/2 times 0 plus 1. Negative 1/2 plus 1/2. Negative 1/2 times 6 is negative 3. Plus 0 is negative. Work column by column, getting the 1 first by dividing, and then you get your zeros, and it should work out. Now, it's a good refresher for all of us, because we have had a 3-day weekend, yeah? Guys, why do I have this awkward space over here in Vico's question? It's like I think there should be a row or something. 3 variables, 3 rows. So what am I going to put? Got it. Do I have my 1? Yeah. Can I go get another 0? Sure. I can do negative 3 row 2 plus row 1. I'm going to do what I normally do. Just that's going to be kind of tagging along the whole time because I can't really change him much, can I? So I'm keeping my 1, 2, 1, 8. Negative 3 times 1, negative 3 plus 3. Negative 6 plus 7. Negative 3 plus 6. Negative 24 plus 26. First column done. Second column, I have my 1. Sweet, so go get zeros. I already have him. Okay, cool. So negative 2, row 2 plus row 1. He's just tagging along. He's fine because he has his 1 like I want him to. Let's go find that first row. Negative 2 times 0 is just 0. Sorry, I keep trying to move it because the numbers start to get kind of squishy. Have you guys noticed that? There we go. Okay, so negative 2, 0 plus 1 is 1. Negative 2 plus 2 is 0. Negative 6 plus 1 is negative 5. And negative 4 plus 8 is 4. Last but not least, get your, that's okay. What are we going to let z equal? Let z equal a. And so then we have x minus 5z equals 4. That's from this equation. And then we have y plus 3z equals 2. And so if z equals a, we're going to plug and chug back to good old substitution. So x is equal to negative 5a added to the other side. And then y plus 3a subtracted from the other side. Vico, I think this should match up. Those of you guys that got it right, maybe just double check us. But I have our x as 4 plus 5a, our y as 2 minus 3a, and our z as. Does that make sense? Why? Yeah. Whenever you have something, and that was one of those last examples that we saw on, I think, Friday. Whenever you have one of those weird, whenever you have one of those weird where it's 3 variables but only 2 equations, throw in the zeros and then dot, dot, dot until you eventually have to just let z equal a. Or vice versa, if you have 3 equations, 2 variables, you let that third column be zeros. And you just go like normal until, okay, let z equal a. Dot, dot, dot. All right, kiddos, with that, those are the questions that I saw. If you have any extra questions, come see me after school. I will only be here today until about 3:45. I have like 2 different meetings after school. Sorry, guys. One's about a mission trip and one's about my small group. So just a warning, 3:45, and I have to run out of here. If we are back in notes section 8.2, and some of you just need to take a deep breath and let it out, this section is a lot easier, okay? This section is a lot easier, meaning I think some of you can tackle this example right now without needing any further clarification, instruction, or examples. Ready, set, find me x and find me y. Ready, set, find me x and find me y. You can collaborate in your groups. It should only take a moment or 2 or 3. You guys looking at? You looking at how they're equal? Ooh. If they're equal, what's going to have to match up? Numbers, right? So do you have any baby little equations that you could be solving right now? Perfect. So anybody think of making 2x plus 1 just equal to 5? Because those 2 spots have to be the same. Some of you have already solved. Careful, not 6 though. 5 minus 1 is 4. Oh. Got it. Gavin was looking at the other one. 3x has to also equal 6. And in his mind, that was probably an easier one to solve, right? What would happen if these two didn't agree? We'd have an inconsistent equation, meaning like it would be impossible. They can't equal. X can't be two different numbers in one situation. So, whew, good thing x equals 2. It matched up. What else do we have? Yeah, we still have the y too, right? So 4 is equal to 3y minus 5. Anybody added to get 9 and then divided? So either way, x equals 2, y equals 3. What was that? Solving a system of equations? No. Good old-fashioned, we're missing something. Let's go figure out what it is. When two equations, I should say, I apologize. When two matrices are equal, the corresponding entries have to be equal. The corresponding entries have to be equal. Let's talk about matrix addition. Okay, don't worry, we're going old school. We're going algebra 2. In order to legally be able to add matrices, we have to, first of all, have matrices of the exact same size. Why? Because matrix addition says add the corresponding entries or subtract the corresponding entries, or even matrix multiplication with a scalar. Well, that one isn't exactly needing two matrices. That would just be one. So for addition and subtraction, we have to have matrices that are the exact same size, or else we won't have corresponding entries. But in number 1, does it make sense if we add a 0 matrix of the exact same size, it'll end up being the same thing? So we could technically call this guy a 0 matrix of the right size. We could call him the additive identity if we want to give him a snazzy name. The additive identity, because any matrix plus a 0 matrix of the exact same size, got it. But what happens when we go down to number 2, cool kids? Two plus 0 is 2, right? 1 plus 1 is 2. 0 plus, can't do it, so therefore, not possible. Oh, why can't we just put in zeros? Because we're not making the matrices. For the augmented ones, we were making the matrices, but not in these ones. So since we're not making them, we have to go with what we have. And if we have something like a 3 by 3, oops, sorry, there you go. If we have something like a 3 by 3 and a 3 by 2, if they're different sizes, we cannot add them. It's illegal. They have to be the exact same size for addition and also similarly subtraction. But maybe some of you are remembering that multiplication doesn't quite work the same way. Multiplication doesn't quite work the same way. So our not possible is our final answer. There is no way to add those two together if they're not the same size. Talk about the basics of what makes two matrices equal. The basics of what or how do we add matrices. So what if I was to give you something like this and say, okay, what would you do if I gave you these two and said, add it for A, subtract it for B, multiply by a 3 for C, and then solve the formula 3A minus 2B for D. I'm going to freeze the screen. I'm going to start playing. You guys start playing too. Add them for A, subtract them for B, multiply by 3 for C, and then plug in and solve the equation 3A minus 2B for D. Now, A, B, and C shouldn't take too long. If you guys remember from last year what you're doing, adding the corresponding entries, subtracting the corresponding entries, multiplying the corresponding entries. You guys agree? 1 plus 2, negative 1 plus negative 1, 2 plus negative 1, negative 1 plus 8, minus 2, negative 1 minus negative 1 plus 1, 2 minus negative 1, negative 1 minus 8. 3a, what did I do? Times 3 times 3 times, exactly. So what am I going to do for, oh, sorry, that was C. Lo siento. However, if I were you, I don't know, once you get to D, it kind of, there's a lot going on. So I think I would maybe make myself a little matrix equation and say, okay, I need 3a, which I just found, which is 3, negative 3, 6, negative 3, minus 2b, okay, which is going to be 4, negative 2, 16, equals. I would just make myself a little matrix equation to go ahead and solve. I think it just makes everything a little easier. Easier on your brain at least. And 3 minus 4 is negative 1. Negative 3 plus 2 is negative 1. 6 minus negative 2 is 8. Negative 3 minus 16 is negative 19. Anybody beat me there? There we go. Not too bad. How are matrix operations for addition, subtraction, multiplication by a scalar, or multiplication by a single number? Not bad, as long as you keep track of the numbers. Cool beans? So what's going on this page? We actually kind of did the scalar multiplication already. Both of these needed scalars, aka constants, to be brought in. But if, as we just saw, scalar multiplication is multiplying each entry by a number, well, if we can come in, what else do you think we can do? Pull out. So if you were to be given some sort of matrix like this, maybe it'd be a lot easier to say, ew, gross, why are they all halves? Okay, maybe that's not exactly our motivation, but couldn't we pull a half out of everybody? So the same way that scalars can be brought in, scalars can also be taken out, but they'd have to be taken out from everyone. So what would be the remaining matrix, guys, if we factored out 1/2? Pause. Good job, Adam. Let me zoom in just a little bit. I think a few people are still writing. Let me get some other volunteers. 1, negative 3. What's the next entry going to be? And then, got it. So scalars can come out, but scalars can also come in. Sorry, there's something weird on my board. Scalars can come out, just like scalars can come in. We've added, we've added matrices. We've subtracted matrices. We've multiplied matrices by a constant. We've even multiplied by a constant, both of them, and then added or subtracted. What haven't we done? Talked about properties, first of all, about what's legal. I don't need you guys to memorize these per se. If this was a higher math class, maybe we'd dig a little deeper into all of these. But long story short, matrix addition, since we're just adding entries, it can go either way. Associative property is still a thing with matrices because since, once again, you're just adding corresponding entries, it's no big deal. Scalars, I could bring in this, well, I could multiply a CD, then bring in, or I could bring in a D and then bring in the C, or I could bring in a C and then bring in a D. Once again, I can have the associative property of multiplication. 1 times any matrix is itself, so 1 is a scalar identity. I can add A and B and then bring in C, or I can bring in C to both and then add. And similarly down here, I can add C and D and then multiply, or I can multiply C, multiply D, and then put together. And then we already talked about the additive identity, how as long as you have a 0 matrix of the exact same size as A, it will stay the same. You don't need to memorize them, don't even necessarily need to write them down. Besides the fact with, well, besides remembering, with matrix addition / subtraction and scalar multiplication, everything is normal as far as the properties you're used to. But everything changes when we talk about matrix multiplication. Everything changes when we talk about matrix multiplication. I'm going to have you guys write down my little way of remembering it from up above as I show the work of multiplying the little example down below. So matrix multiplication, a little bit more complicated because we're not just bringing a scalar, we're not just bringing a single constant into every entry. Now we have two separate matrices that need to be brought together. And if you want to think about it, a monomial times a binomial, trinomial, etc. was easy, bring it into everybody. But as soon as you have binomial times binomial or binomial times trinomial, oh, stink, it got harder. It's very similar here. My way of remembering it is cross down. When you're multiplying A times B, you go across A as you go down B, and you pick up corresponding pairs along the way. First with first, second with second, third with third, etc., adding them. So for A sub 1, 1, you need to multiply and add row 1 with column 1. A11 needs the first row and the first column all put together. So the first row of A with the first column of B, and we take together, or we multiply together, multiply then add, multiply the first plus multiply the second, so you can keep on going. Multiply the first, multiply the seconds, then keep going. A12 is going to be very similar, but for A12, I'm going to multiply, add row 1 with column 2. Because of our notation, row then column. I'm now going to do row 1 with column 2. Multiply, add, multiply, which means -1 times 2 plus 3 times 1. Other teachers in the past that I've seen teach this literally have the kids putting their fingers on the first row, first column, and saying multiply. 3 plus multiply. -12. 3 minus 12 is -9. And they're exactly right. You could write it out like a little formula, or you could actually just do it in your head mental math. 3 minus 12 is -9. The same way as 3 minus 12 is -9. Then you would go cross down and then cross over down. Multiply, -2 plus 3 is -1. Just like -2 plus 3 is -1. I could keep on writing little equations, like now it's time to go second row, first column, second row, second column. So I'd have 4 times -3 plus -2 times -4. Then I'd have to go second row with the second column. 4 times 2 plus -2 times 1. I'm writing 1 out the long way, just so if you need to come back and review, you can see where all the numbers are coming from. I think it's really helpful to write out at least one long way as to everything that's going on. Now we're in row 3 of my answer matrix. So I take the third row, the first column, 5 times -3 plus 0 times -4. Now it's time to do third row, second column, because I'm in the A32 spot. 5 times 2 plus 0 times 1. So if at any point when you're doing homework, or if at any point when we're talking about matrix multiplication in class, maybe you should highlight or star this example, come back and review, okay, how did we get our numbers? We got the -9 by multiplying first row, first column, 3 minus 12. We got the -1 by doing first row, second column, -2, 3. Now we have it written out, but can you guys get to the second row, first column by doing the second row, first column? -12, 4 times -3, -12 plus 8. -12 plus 8 ends up being -4. And then 8 minus 2 ends up being 6. And then we would go to our final to get our third row, first entry, third row, first column, negative 15 plus 0. Third row, second entry, third row, second column, 10 plus 0. So our final answer is negative 9, negative 4, negative 15, negative 1, 6, and 10, which is a 3 by 2. What were the sizes of the original matrices? Were you guys paying attention? Our answer is a 3 by 2, but what were our original sizes? There's something to do about when this is legal and when this isn't, because some matrix multiplications aren't legal. Good. This size is, careful, wrong way, 3 by 2. This one's a 3 by 2. And what's this one? A 2 by 2. What needs to happen for us to be able to multiply? Yeah, the two insides need to be the same. The number of columns need to match the number of rows. The reason being the number of times I go over has to match the number of times I go down. Or else I'm going to be trying to do this and I'm going to have one have an entry and one not. That's illegal. So my middle two have to match. And check it, guys. Do you see who's outside? What's outside will always be the order of the answer. What's outside will always be the order of the answer. So you could actually start off with a matrix being like, hey, I need to fill in 3 rows and 2 columns. That might help some of you. I need to fill in 3 rows, 2 columns by using my multiply add pattern of going across as you go down. So with that, can you guys find me A times B? But first of all, see if it's legal, because if it's not, well, if it's not legal, well, stink. Who wants to start that, huh? Nice thing is, kiddos, this homework is not due until Thursday, but careful. We're only spending a half day tomorrow on 8-2, basically continuing to practice matrix multiplication and make sure that you guys have it. So we are starting on section 8-3 tomorrow, so your goal is to get as far in homework tonight as you can. Some of you might be doing little baby formulas, and that's not bad. Some of you might actually be adding together. But hopefully you guys are seeing 0 minus 4 plus 2. Maybe some of you, even though you're not going to write everything, maybe it's a good idea to at least write what you're doing, 0 minus 4 plus 2, just to kind of keep track so you don't lose something. Oh, did you guys figure out, is it legal? Yes. He's a 3 by 3 and he's a 3 by 2. So those are going to match, so I'm good to go. What's my answer going to be? A 3 by 2. All right, cool, kids. We'll finish this up tomorrow, but some of you might want to review just a little bit, although from what Adam said, it won't be in notes from last year. It'll be in worksheets if you can find them. Or talk to an Algebra 2 kid and be like, so I know you did this recently. Can I see some of those worksheets? But practice. Go look at the examples in the book. I'll see you guys later. Chapel.